So Josh is out of town. He's on some conference. I don't know which conference he is, but so I'm giving a lecture. Last lecture we learned RW metric. We usually call FRW or FRW metric. So this metric is quite same as special relativity, but we have this RT, right? What is RT here? What do we call this RT? Yeah, scale factor. So this coordinate we call co-moving coordinate. So co-moving coordinate doesn't change due to the expansion, but RT has the information about the expansion. So we measure the light from the past, and that light, the wavelength of that light is stretched by the expansion of the universe. So we measure the redshift of the light. So we connect this redshift to the scale factor, which describes the expansion of the universe. So redshift is connected by RT naught, which is today's scale factor. And today's scale factor is 1. And over RT, so that's equal to 1 plus z. And also we connect this Hubble constant to this scale factor, which is the rate of the expansion divided by the scale factor at that point is Hubble constant. So we will see a lot this Hubble constant, and we will connect this Hubble constant to the age of the universe today. By the way, today's colloquium is about storms on Titan. So it's the joint colloquium with EPS department. And problem set 10 will be up by tonight. So this metric describes the space of time of the universe. So what we want to know about the universe, what we learn from the cosmology. So the key question about cosmology is, what is RT? So as I said before, this RT describes the expansion of the universe, so dynamics of the universe. So, and this RT is determined by what we have in the universe, or what consists of the universe. So what derives the expansion, or what decelerates the expansion, is matter. What do we have matter? What kind of matter do we have? Yeah, baryons, dark matter. And also some energy also derives this RT. So some energy affects RT, which is radiation. So can you connect this the energy of the radiation to some mass, some equation? Yeah. So using this, we include radiation to describe this RT. So radiation includes photons and neutrinos. We will talk about this later, not this lecture, but later lectures. And recently we found out dark energy, which is some, sorry. Maybe I thought if I play the slideshow, then it wouldn't happen. It will happen every 5 minutes, so let me fix it. It's my niece. So recently we find there is something weird energy. We don't know it is really energy or a matter something, but dark energy also derives RT. So to solve this RT, so if we want to know exactly how RT changes as time changes, then we need to solve. We need to use GR, including all these matters' behavior, and we have field equation, Einstein's field equation, but it is really complicated to solve. So there are only a few solutions about Einstein's field equation, but we have some assumption, which is so we have this assumption, which is called cosmological principle. So that means universe is homogeneous and isotropic. So under this assumption, we can reduce the complicated Einstein equation to easy form, which is called the Friedmann equation. But before that, what is homogeneous and isotropic? Yeah, it's same everywhere in every direction. So that means we are not living at some special point in the universe. So everywhere is same. So we are not living at the special direction. The illustration is, my keynote doesn't work with, so as I said, universe is, I don't know, just I should show by this. So in local universe, it looks like very anisotropic and not homogeneous. But if we go further, if we consider very large scale, so on large scale, universe is homogeneous. So we learned the velocity dispersion of the cluster is about 1,000 kilometers per second. So we should go beyond that scale. So about 100 megaparsec scale, universe looks like homogeneous. So if you draw some sphere about 100 megaparsec and some place, and you draw another sphere at another place, and the mass in those spheres are same. So there is no preferred direction. And also, if we look this direction, or even though we look another direction, the universe looks like same. That means isotropic. So one illustration is this. So if you look at this represents the homogeneous, but it's not isotropic. Let's assume we are at this center. And if you look any point, the blocks are uniform, right? But if you look this direction, the blocks are aligned in this way. But if you look this direction, blocks are aligned in this way. So there is something different if you look this direction or if you look this direction. So it's not isotropic. But if you look at this figure, assume you are here at this point, and if you look any directions, it looks same. But nearby, it's really dense, but further out, it's not dense compared to the center. So it's not homogeneous. So whenever we describe something about homogeneous but not isotropic, usually this example comes up. So this shows something like homogeneous but not isotropic, but this shows it's isotropic, not homogeneous. But our universe is homogeneous and isotropic. So next shows this is the initial condition of some n-body simulation. So we start with this matter fluctuation at redshift about 100 and evolve today. These bright spots are over dense region, and these dark spots are under dense region. But if you look at this very small scale, it's not isotropic or homogeneous. But if you consider these large blocks and draw a sphere here or a block here and draw a box there, and you calculate the mass inside, then it's same. Or just consider that if you smooth this density field with that kind of large sphere, then it looks like just uniform distribution. So this is the example of uniform universe on large scale. So under this cosmological principle, and actually in the past, people were talking about like, is the universe is really homogeneous or isotropic, and they go out measure, and from the observation, people start to think, oh, universe is really homogeneous and isotropic. But now these days, people are working on something non-Gaussianity, something is weird, and that derives not an isotropic universe. So people try to measure very, very small anisotropic, but from CMB or from other data, right now in some error bar, we see universe is homogeneous and isotropic. So it's from observation. So now we have field equation, what we call Friedmann equation. So this is the reduced Einstein field equation. We call this Friedmann metric equation. I usually call just Friedmann equation, but this guy also solved this equation too. And what does it look like? What does this term look like? It has velocity here. Can you connect this term to? Not really. Something energy. Yeah, it is related to the kinetic energy. And how about this? It contains G and rho. Yeah, it's potential energy. Then what's this? So it's like sum of kinetic energy and potential energy. Yeah, total energy. So it's related to total energy. And this rho has physical unit. What is the unit of density? So, yeah. So mass or volume. And this rho contains mass, which is m, plus the energy. We talked about photon and neutrino, which is energy divided by mc square, or energy divided by c square. So this is from photon and neutrino. So it looks like an energy equation. So we will talk about what this K means, but before that, if you have some negative total energy, what does the orbit look like? If you think about some energy equation for the orbit, it's bound. So if energy total is larger than 1, it's bound. And if it's negative, then it's bound, right? And energy is larger than 1, the orbit was hyperbolic, right? So it's unbound and go infinity forever. And if energy total was 0 and it was parabolic, right? So we can connect this to the geometry of the universe. So if K is negative, that means this right-hand side is positive, right? That means right-hand side is positive. This is unbound orbit is corresponding to open universe. The universe just expands forever. But if we have a positive K, that means the right-hand side is negative energy. This means bound orbit, which means the universe will be collapsed at the end. So this term is related to the geometry of the universe, or curvature of the universe. If the universe is flat, then what is K? Yeah, flat universe. The curvature is 0. And by observation, now we about 99.9% believe the universe is flat. So later we will learn some universe which is not flat, but our universe is flat universe. But if you see this equation, it looks like you may think it is easy to solve. It's just this differential equation, and the square is here. But actually, this rho, the density depends on the scale factor, and this density depends on differently on the mass. So if you have only mass, then this density depends on some r to the power, or if you have some other stuff like radiation or dark energy, then this density depends on the scale factor differently. So it's not that easy to solve this equation. But later we simplify the equation and we will solve the equation. And also this scale factor depends on time. That means the universe is not stationary. So we are very familiar to the expanding universe, right? Right now, it's not that weird. But in the past, people didn't like the expanding universe. When we really go back to the past, like people didn't like the sphere, Earth, and the Earth is rotating around the sun. They didn't like this idea. And likewise, people didn't like the idea of the of the universe, expanding universe. So Einstein introduced so let's just assume flat universe. He introduced this cosmological constant. We call it lambda. And this lambda cancels out the matter inside of the universe, so it doesn't make the universe expand or collapse. So he included this to the equation to make universe stationary, but later, about, I don't know, a few years later, Hubble published a paper, the universe is expanding by observation. So he thought, and he made statement like this is his great bundler, so it is big mistake. So it was my mistake to include this cosmological constant. And also there is another problem. Like if we don't have any matter, and if we have only cosmological constant, then the universe expands exponentially. That's the current universe. Like the universe doesn't expand exponentially right now, but if the lambda start to dominate, the universe start to exponentially, universe start to expand exponentially. So this has a lot of, looked like, this term looked like a lot of problem, having a lot of problem. But right now, this is also very natural to include the equation to solve the evolution of the universe right now. Because we observe cosmological constant. The first observation is from supernova type 1a. So they measure the light curve, the luminosity of the supernovae, and it's dimmer than we expected. That means, and the universe is expanding faster than we thought. And also CMB data comes out, which is more cracked, and that says we have something, not just normal matter or dark matter, we have something different. So now it's observationally confirmed we have cosmological constant, or people still argue about, is this really cosmological constant deriving accelerate the expansion in accelerating universe. But people think about this is really constant, or it changes by time, or it's another form of the gravity. People still argue about, but the observation shows like in some confidence level, it's mostly consistent with cosmological constant.
Mm-hmm. Does Einstein also change the form of the equation, that the drdt is squared, but not the 1 over r? Or is that?
Say it again.
So over there, 1 over r.
Oh, right.
So
sorry. Typo. So we are going to derive this using Newtonian physics. So we got to know this equation is corresponding to this kinetic energy, potential energy, and total energy. So let's start with something familiar set. So let's consider this sphere, and the distance from the center to here is scale factor times r bar v, which is co-moving coordinate distance. So it's just a physical distance, and or a proper distance. And this term is fixed. And there is some point mass m. Some test particle is here. And the total mass inside of the sphere is large m. And then we can write, and also this sphere, let's say this sphere is expanding. So the expansion velocity Then what is the kinetic energy of this m, this small m? Yeah, 1/2 mv squared. So it's moving by expansion velocity. So the kinetic energy of this small particle is 1/mv squared. And what is the potential energy for that particle? Speak up. Yeah, big M, small m over RT over R bar V is like total energy. So we have this energy total at the beginning. This is constant. So because there is nothing external force, there is no external force. So energy total is constant over time. And then let's describe this V, because we know this R bar V doesn't change, but RT change as time passes. So let's connect this V. V is dr dt, like the change of the distance by time, right? So dRT, R bar V, dt is the velocity, right? Then just this doesn't depend on time, only this depends on time. And to write easily, I will say the large R dt is RT dot or R dot. And what is this large mass in terms of the density? Just it's a sphere, 4 pi over 3 R cubed, and the density. And in the book, we use only cold dust particle, which has mass, but which doesn't have pressure. But here we are including everything. So this density is including radiation, mass, or anything. So it doesn't matter, just we are writing raw total. Now also it depends on the time too. And then we write this, is it moving? So now we have these two equations and we write then on half m R bar V R dot square minus G 4 pi over 3 R bar V R cube rho total m R bar V R is equal to E total. And just rearranging this. So I'm going to divide by m. I'm going to divide this equation by this small m, so what we can write. Multiply 1 over m, then this equation 1 over 2 R bar V R square minus G 4 pi 3 R, and this goes away. So it's cube and it's just 1 power, so it becomes square. So 4 pi G over 3 R bar V R square rho total equal to E total over m. And what I'm going to do is to make the same form as Friedmann equation, which is behind of this blackboard. And let's multiply 2 over R bar V square. Then it becomes R dot square and 4 pi G over 3 A pi G over 3 R square rho total r square is 2e total over m r bar v square. Does it make sense? Then I'd like to organize this with this r. Then this term becomes r dot over r square negative 8 pi g over 3 rho total r square is, let's define this term, negative kc square. So what's my mistake? I should written this Friedmann equation this side. So now we have the same form here, right? And this k so this k is negative e total to e total mc square r bar v square, right? So as I said before, positive energy means unbound orbit, which is speed of light. C is speed of light. So negative energy means positive k, and positive energy means negative k, and that determines the geometry of the universe. Or curvature. So when we describe curvature, it is 1 over r squared, 1 over some radius square. So if we look at this equation, then the top is energy and the bottom is energy too, right? So we have only this co-moving coordinate. Co-moving coordinate is some physical length unit, right? So the curvature, which is k, which describes curvature, that is 1 over length square. The unit of k is 1 over length square. And if we look at this equation, r doesn't have any scale, but this is r dot. So it is 1 over time square. So this is 1 over time square. And also we know the free fall time is 1 over square root of 0. So this is also, this doesn't have any unit, and this means also 1 over time square. And the right-hand side, k is 1 over length square, and c square is length square divided by time square, so the unit makes sense. O is just 1 over time square. So now we have this Friedmann equation from the Newtonian universe. And actually, this derivation has one problem, one very significant problem. What's that? What do you think? What is so the equation is correct. The equation we got is correct. But there is only one different setting at the beginning from the real universe. What is the difference? Think about the cosmological principle. What was the cosmological principle? Yeah, universe is homogeneous and isotropic. So there is no special point. There is no center. And everywhere can be center. But here, there is specific center in this derivation. So this derivation is actually not exactly the same as our universe, but it works pretty well. So just keep in mind, this setting has some special point, which is the center. So just I will write down about the k, which I told you a lot. So it might be bold. to hear about more, but we will.
What about special relativity? Josh mentioned that things are expanding at relativistic speeds, so does that need to be a part of the equation?
So that's the different point, because the universe itself, the coordinate itself is expanding. So it's not quite, the matter itself is moving faster than speed, not faster than speed. Question?
How can we use boundary velocity as the kinetic relativity space that's expanding?
So it's kind of, so we think, so here it's not the universe. Just we have some sphere, so this sphere's surface is expanding with that velocity, and that this matter is just moving with that velocity. So it's not the coordinate is expanding. So it's kind of some analogy, but it's not exactly one-to-one correspondence. Does it make sense? Still confused? I mean, so this is Newtonian sense. So, but we can just connect something we know to the universe, the weird behavior, which is very unfamiliar, and then connect these two and try to understand better. So just I will write down case. Oh. And then tutor expand forever. Not expand the square. And k is 0, and energy total is 0, and it's expand. But at the end, if we think about infinite time passed by, then the velocity approaches 0, and the universe will have finite size at infinity. And k is larger than 0, then energy is less than 0, and it's will collapse. So this is our universe. But our universe is flat, but as we will learn later, the universe expands forever due to weird dark energy. So is it okay I just move this blackboard? No. Maybe I will rewrite the equation. Any more questions? No? So I will rewrite the equation. And now we will talk about just our universe, which is k is 0. This is 0. So, by the way, do you remember what is the definition of the Hubble constant? So actually, it's not constant because it changes as time changes. What is the definition of Hubble constant? Yeah, it's age of the universe, but in terms of scale factor.
R dot.
Yeah, R dot over R is H. So this is basically H squared. And so this is H squared negative 8 pi G 3. And if we have this flat universe, we say we have some critical density. So why we just call this critical density? I mean, it's really hard to make completely flat universe. if k is slightly larger than 0, then it will expand, it will recollapse. But if k is slightly smaller than 0, then it will expand forever. But if we want to have flat universe, we need to have just right amount of the mass. So that means we have critical density. So critical density is defined by, just set by this k is 0. So just writing this, rho crit is 3h squared over 8 pi g. And we use this rho crit a lot to describe the actual density. So if actual density is same as critical density, then we have the flat universe. But if actual density is less than critical density, then we will have open universe. So we compare our actual density to this critical density. So we define that to omega actual density divided by critical density. So this is density. And by calculating something we measured h, rho crit is 9.7 times 10 to the negative 30 gram per square centimeter. Or if we write in terms of kilogram per meter, then it's negative 27 kilogram per meter square. It's so small. So just we don't get any sense from just this number. So let's connect to this to the hydrogen mass. So what is hydrogen mass? Do you remember?
1.67 times 10 to the negative 27.
Yeah. So this is hydrogen mass. So compare to this number to this number. Compare this number to this number. So if we have like about 6 hydrogens, per meter cube, then it will be rho crit. Right? So if we have more than 6 hydrogens per cubic meter, then the universe will collapse. If we have less than 6 hydrogen per cubic meter, then universe will expand forever. So this is very sensible number, I think. Like 6 hydrogens per cubic meter. It's really, really it looks like there's nothing, but it's enough to make universe flat. So we measure this omega from CMB, or there are many ways to measure this omega baryon or omega dark matter and omega total. So by measure this omega baryon, which is a luminous matter, so anything, gas, stars, what else? Something dark, but we know that they are baryon, like black holes, planets, and everything we know. That's 0.04. So visible universe is really tiny. We see only very tiny part of the universe. And dark matter, that's 0.23. So total matter, which has mass, so that's total matter, 0.27. But I said the universe is flat. But we have omega m is less than 1. Omega total is less than 1. But universe is flat. then what's the other component? What's the other energy density? Yeah, so that's dark energy. So we have dark energy, which is 0.73. So most of the universe is dark energy. But this, make sure, this is today. This is today value. So right now, in our universe, today, our universe, this is 0.04, 0.23, and 0.73. But if we go back, if we go to the early universe, then this omega value changes. Because these, all of them don't depend on scale factor in the same way. So they depend on the scale factor in different way. And also, rho crit is defined by Hubble constant, which changes as time changes. So everything depends on time. So this is current value. Then now let's solve this equation under the simplest setting. So here we assume universe is flat, which is our universe. And we have only matter which has mass. So omega m is 1. So we have universe is flat and we have only matter. So to flat, omega should be 1. The density should be critical density, and we have only matter, so omega m is 1. So we will solve Friedmann equation under this assumption. So to get some space, I will move this to here. So this can stay. So we won't think about dark energy. There is no dark energy. So now we solve this equation just assuming we have only matter. So no dark energy, no radiation. We have only pressureless matter. So matter only. Because if we have only matter, then the mass is conserved by time is the same as right? So it's from mass conservation. So mass in the past is just same as the mass we have now. So we will use this mass conservation, and we know just by definition what is this R naught today. This naught means just today, not it's not at t equals 0, but it's today. So this is 1. And this rho naught is also rho today. So this rho t the density at today divided by scale factor. And if we connect this to the redshift, what is scale factor in terms of redshift? Yeah, 1 plus c, 1 over 1 plus c. So scale factor decreases, that means redshift increases. So it's flipped. So it's rho naught q. So we have only matter, and we have this matter conservation. So we want to solve this equation under that assumption. So the k is 0, and just rewrite. Right? Just here, k is 0, and we made r dot square is just left, and everything else is on the right side. And from this rho naught is today's value, so it's constant. By the way, the k was constant. Just I forgot to mention that. So this rho naught is constant, but this is varying. So we want to solve for RT, which is our interest. We are most interested in this RT. So replace this rho t with this. So RT cube from this rho t and this RT square from here. So 8 pi g over 3 rho naught r t. Oh, I got a square here. Are you following this? And this r dot t was dr dt, and just taking square root, and this whole thing is constant, 8 pi g rho naught over 3, and we have RT. Oh, yeah, it's reversed. So now it's just simple differential equation, so we can solve this. So move this RT to left-hand side, and move dt to right-hand side. So square root r dr is equal to 8 pi g rho naught over 3 dt. And we will integrate from when the universe was born, which is scale factor was 0, to some time. And we integrate this from the universe was born, which is t equals 0, to some time t. So then we get so RT is 6 pi g rho naught third power t to the 2 third power. So R just goes as time. So it's not linearly proportional to the time. So scale factor is proportional to t to the 2/3. So So if we don't have any matter, then just universe was born and it will constantly expand. So just we have this linear relation between time and the scale factor. But if we have some mass, then how did it look different? How does it look different? So this is what? Yeah, it slows down as time passes, right? So if we go back, then it was actually faster. It expanded faster before. So if this is the age of the universe because this scale factor was zero. So if this is age of the universe, then if we have matter inside, is the age of the universe shorter than this case or larger than this case, smaller than this case or larger than this case? Age is larger or smaller? So I will give you 1 minute to talk to your buddy next to you and convince your opinion. And I will, or 30 seconds. Does it? So what do you think? It's if we have matter inside, is our T naught is larger than this large T naught or smaller than T naught? What are you? Larger? Are you sure? It's shorter because if we have mass inside, then that mass decelerates the expansion. So that means we have faster expansion at the beginning. So we have some value. We know what is H naught by measuring the today's value. So we need to match this. And we know the size of the universe right now. So we need to match. We know this R and we know this slope. And then we just extrapolate back to this time. And it was actually faster than right now, so we have shorter age, the smaller age of the universe, compared to no matter universe case. So today our T naught is 1. So Hubble constant dr dt over r, and r is 1. So Hubble constant is this slope. So we should match this slope and this r, and then extrapolate back. So this is for different cases of universe. Here we are not talking about dark energy. We are talking about only matter universe. We have only matter, but here we have critical matter, then we have this yellowish line. But if we have more than critical mass, critical density, then universe will turn around at some point and will collapse. So we call this is big crunch. And when I was undergrad, it was quite interesting, but now it is not interesting at all because we know it won't happen. So because I mean the cosmology is really developed very fast. So, I feel I'm old. So, and if we have less mass, then we have the curve in between no mass and this critical mass, and it will expand forever. So here also we know this scale factor today and the slope today, so we match everything at this point. So if we have more matter, then the universe is very young compared to we have less matter.
The theorists believe that there can be a universe that is completely empty. Does it even make sense for space to exist without things in it?
That makes sense.
It does?
It does make there. I mean, there could be a space without any mass inside. And also, like, if much time passes by, and dark energy is too dominant, and the universe expands very, very fast, so the universe is really, really big compared to the mass inside, then probably it can be considered as empty universe because the mass is too low compared to the volume. And so we have something weird, dark energy. So somehow, coincidentally, the age of the universe is quite similar to the empty universe, so which is 1/h0, even though we have some mass inside, somehow due to the dark energy. So our universe, omega matter, is 0.23, but we are living in the flat universe due to the dark energy. So if you see this, so this dashed curve is only matter universe with low density, which is 0.27. This is critical universe, sorry. So this is the dashed line shows critical universe. We have only matter and flat universe. And this solid line shows the flat universe, but with something weird, dark matter and some matter. So if we look at this this dashed line only, and it's constantly decelerate a little bit. So it will expand forever, but at the end, the velocity will be 0 and the size will be finite. So we see some constant change in the slope, but since we have dark energy, so before today, we have kind of similar tendency of this to this dashed line. So it was decelerating as time passes by. But today, somehow, it is also called coincident problem. Dark energy start to be dominated. So the universe now is expanding very fast. Expansion is accelerating. So it's not. It's also no matter universe is this constant line, but now it's above the constant line due to the dark energy. So later we will learn. At the beginning of the universe, the radiation is dominated because radiation behaves differently from the matter, and in some ratio, in some history of the universe, the matter was dominated. So we can consider the universe as omega matter is one universe, which we solved before, and now the dark energy start to be dominated. So it's quite different from omega matter equal one universe. But people don't know how human being was born in dark energy dominated universe. Somehow, I mean, people think that's somehow related.
So that puts us at like an inflection point on this. Like, so we're sort of, that seems
Yeah, so we will calculate later, but like at somehow this point are kind of start to be dominating. So, but it's about redshift 0.7, which is really nearby universe. So it's really constant. We don't know why we live in that universe. And, oops, that's that. So just to repeat, the slope today dr dt today is Hubble constant, which is dr dt over r, which is 1 today. So the slope was the Hubble constant. So the age of the universe without matter, so there is no matter, then it was, let's say, T age matter 0. So coincidentally, our universe is 1 over h naught. The age of our universe is h naught. But if we have only matter, so and the universe is flat, then what is the age of the universe? I need this. And we will calculate the age of the universe, and also if we observe when we observe our galaxy, we see it or something. So again, we assume the density is critical density, so the universe is flat, and we have only matter, so matter only. So from this equation, we want to connect to the redshift. So redshift is, what is redshift? How does the redshift relate to scale factor? Yeah, 1 over 1 plus e. Don't forget 1 over 1. Its inverse is 6 pi g rho 1/3 T3. Just checking the dimension. The redshift, does the redshift have dimension? No, it's unionless. And g rho, do you remember what is free fall time? Yeah. Free fall time is 1 over square root g rho. So this is the unit of time. So g rho is time to the negative 2, right? And we have 0, 1/3 power, 1/3 power, so time to the, negative 2, 3. So this dimension is cancelled with this, so we have unitless on the right side too. So this equation makes sense, it's unitless. So just rewrite this like this. The time is 1 plus z to the 3/2 6 pi g rho naught 1/2, negative 1/2. So this is age at z. So this is the beginning of the universe, and now we are here. So if a galaxy was here, it was redshift something, then this t tells you the age of the universe at that point. So today, if we plug, so today the redshift is 0, right? Or R is 1 by definition. So by plugging z equals 0, then we have age of the universe today, which is 6 pi g rho negative half. So this is the age of the universe at redshift 0 and the flat and matter only universe. So when we had that curve here, so this is no matter and this is a matter case. So this is 6 pi g rho naught 2. And from we learned the look back time before, right? Do you remember that? So look back time is this. So how far is this galaxy from us? So delta 2t look back time is just, what's that? Having these two information. So just the age of universe today minus the age of the universe at z. So this is 6 pi g rho naught to the negative 1/2, negative a half, and 1 minus 3/2. Does it make sense? So t look back time is this. And we want to connect this age of the universe with Hubble constant because we know this is 1/h0. So to connect this, let's use this value. Rho critical is just if I rewrite h squared negative 3 8 pi g over 3 rho critical is 0, right? So today's density is matter only in matter only universe, rho critical naught, which is h naught squared times 3 over 8 pi g. So we use this, and also let's use this. So today our t is 1, right? And 6 pi g rho naught 1/3 is, let's say, t naught negative 2. Does it make sense? Are you guys following this? So just rewrote this equation, or rewrote this equation. I wrote t naught, it's th at z equals 0. So just rewrote this. Then I'd like to write rho naught in terms of t naught. So this is 1 over 6 pi g t naught square, right? So we know this, and we know this. Then combining this, 1 over 6 pi g t naught square is equal to h naught square over 3h naught square 8 pi g. So I want to describe this t naught in terms of h naught. So I will make t naught on the left-hand side to everything as right-hand side. So just to make it easy, 3h naught square 8 pi g times 6 pi g. So this pi g goes away, and this is 3, and this is 4. So 9 over 4 h naught square is 1 over t naught square. So t naught is now, we should flip this. So 4 over 9h naught square root. So that the age of the universe is 2 over 3h naught, which is less than 1 over h naught. So if I rewrite this, no matter universe was 1 over h naught, but if we have matter, if we have critical density with matter, then this, the age of the universe is 2 over 3h naught. Does it make sense? So the age of universe with matter only is less than this. So it's almost time, and that's it. And next Tuesday, Josh will be back, and you will get more fun lecture because he's more humorous than I am. I can be humorous in my language too.